Okay, let's get started. So I can't answer any specific questions about midterm problems because there's one person who had extenuating circumstances and is writing the exam slightly later. But I can make general comments about the difficulty and how people did on the midterm. Does anyone have any thoughts about the midterm?
Is it going to be curved?
Well, so the end grade that you get, the final grades are going to be curved very significantly. I'm not a fan of curving individual pieces of homework. Although there is a people writing reviews reason for me to do so. So perhaps I will curve the midterm. Although once again, whether or not I curve the midterm individually doesn't affect your final grades in the slightest because I'm curving final grades at the end. So the answer is yes, although maybe not the midterm grade itself. I should mention that last summer, I taught a really experimental course which hadn't previously been offered at the university. It was an advanced class, and so the people were highly motivated, and I could ask them to do a lot more work than I'm asking you to do. And really, I had free reign and I could do whatever I wanted. Now, given those circumstances, I didn't give anyone less than a B- in the course, and only like 2 or 3 people got B-. Now, this isn't an advanced class, so I'm not promising that I won't give anyone less than a B-, but I'm generally not a fan of destroying people's GPAs. And now I should say one more thing about the midterm, but well, I guess first I'll let anyone ask any other questions or comments before I say what my opinion was of the midterm. I've looked over all the responses.
Do you have an idea of what the average is yet, or is that going to come when you start really grading it?
Oh, so I can't say what the average is and be not off by 10 to 15%. But the average is certainly a lot better than homework 1. I think that's okay. I have no idea because there are some later questions that were done poorly. And I don't know to what extent that affects people. What I do know is that almost everyone submitted some amount of very good work. So averages don't matter, but it's not the case that there were people who just couldn't do anything. Almost everyone submitted several problems that were done very well, which is what I care about. Let's say the average might be 60 to 70%, which is good. Right. So I'm pretty happy about how people did on this midterm. I've TA'd calculus a large number of times, and the work that I was getting on this midterm was better work than one usually gets in this course, considerably better work. Also, everyone properly formatted their assignments in terms of taking scans and submitting a single PDF file, which is amazing. I asked you to, and I threatened some penalties for style marks, and guess what? Everyone did the right thing as a result. So that worked very well. But apart from just looking nice, everyone did some things appreciably, and I think that about more than half of the people, more than half of the responses, did almost all of the questions on the exam. Well, more than 50% of the questions on the exam pretty well. So they learned, that means in order to have done that, you would have had to actually learn a fairly large number of things, because each one of the parts, let's say 2-part problems, there were a bunch of 2-part problems. Each one of those requires learning some specific trick and some specific manipulation. And if you're getting half of those, that means that you've learned half of those tricks and manipulations, and also they're being written correctly. People are writing the square brackets, they're putting in the formatting, they're showing their work, they're writing strings of equalities, they're not misusing implication and equal signs, which makes me happy. So I'm pretty happy today about the work that I saw, which reflects well on final grades. If I'm generally happy about how people are performing, then I'm comfortable curving grades to a higher level. So good work. More than half of the responses that I saw were excellent, so that's good. And again, my goal was to get people to write good responses. Now, before I toot my horn, I should admit that the more likely reason that I'm getting good responses is that about 40% of the people originally enrolled in this course withdrew after the first week. So there was a selection bias occurring there. And that is the more likely explanation for why the responses that I'm getting are better than in a typical B class. But if you are the average person in this class, then the following statement applies to you. You have submitted better work than one generally sees in this course. Does that sound good?
Yes, thank you.
Now, okay, I had a bit of a cold over the weekend, and every single time I teach a lecture, I think that I'm going to run out of material for 3 hours. This time, I've always thought that it's like almost 95% certain that I'll run out of material, but this time I'm 99.9% certain that I won't have 3 hours worth of material. And you've done the midterms, so we're probably going to end early, and we can do 2 breaks to pad things out. Okay. Also, a reminder that homework 3 is due on Wednesday at midnight, so tomorrow at midnight. Okay. So last time we were discussing area and area problems. Wait, so no one else has any questions about course procedures? Well, can anyone tell me what they generally thought of the level of difficulty of the problems on the midterm?
I thought it was pretty fair.
I designed it to be slightly easier than the assignments. So the assignments ask you to have more tricks. There were fewer problems that had tricks, and then it was about the length of an assignment, which is a bit longer than I originally said, but I tried to make it as fair as possible to do in 24 hours. So that's good. Anyone else?
Going from the midterm to the final exam, is the final going to be cumulative, or is it going to just have the material from now until that point on it?
I honestly think that word problems are sort of boring. And I would not want to give a final that consists entirely of word problems. So it's going to be cumulative for the reason that it would be bad otherwise. But that being said, I think of the material as theory and then applications. So knowing how to solve integrals is the theory. So you can't unlearn how to do integrals. And I haven't written homework for yet, but I am going to put some integration problems on it. They're going to be slightly more difficult integration problems than the previous assignments, but they're not going to be on anything new. So the problems are going to be there so that you don't forget how to do integration in the 2 weeks that we have remaining in the course. And then on the final, there are going to be more integrals. But I think that the main problem-solving skill that you learn in this course is how to compute integrals, which is what we've been doing for most of the course. Okay. So should I start? No other comments on the midterm? Okay. Let's get started. So I'm going to start on a slightly more interesting / high note, and then we're going to backtrack to the material that we were doing before. At the beginning of the course, on the first lecture, I spoke about how Eudoxus determines two circles are to one another as the squares on their diameters. In calculus textbooks, they sometimes blatantly state the wrong thing and say that he proved a formula like a equals pi r squared. But let's do our own Eudoxus thing and determine what the area of a circle is. This is the modern version of what Eudoxus did. So what is the area of a circle? And we're going to determine this via calculus. So it's going to be the circle of radius r. In particular, what is the area of the region bound by the curve? And then we're going to say x squared plus y squared is equal to r squared. So r is going to be the radius of the circle. This is a circle of radius r. And then now a very good way to start any problem about volumes or areas is to draw a diagram. So we're going to draw a picture of what this looks like. This is always a good first step. Now, in some cases, there are going to be functions which you don't know how to graph. And then it might not be a good first step to draw the pictures. But if they're basic functions, such as the relation defining a circle, well, it's not a function, it's a relation, then you know how to graph this. So it's always good to start with this. So again, circles are hard to draw, so this is my approximation of drawing a circle. Then if I mark this coordinate right here, which position along the x-axis is this? What value? So what are the bounds on this circle given by this equation? Well, if y is equal to 0, then what is x equal to if this equation is satisfied?
R.
Yeah. Okay, now what we're going to do is we are going to find the area by summing up vertical slices. By integrating vertical slices. So in other words, let's suppose that we have some value here, x. Then we have a certain height over x. And it would be good to determine what these points are. What are the coordinates of these points? So if the x coordinates is x, then what is the upper y coordinates? In other words, solve this equation for y.
Root R squared minus X squared.
Good, thanks. And then, so the upper position is the positive version of this, and then the negative position is the negative version of this lower position. So in other words, we have that's the height of the vertical slice over x. Is, and then we can write h of x, so it's a function of x, and then it's 2 times the square root of r squared minus x squared. And then from before, we spoke about Cavalieri's theorem, and we said that if you have all of these heights, then you can sort of rearrange them so that you get the area under the curve. So in other words, for example, if this is the semicircle right here, then we can sort of take the circle, we can shift it up, and we can get twice this function. It really goes up to here. And then we can integrate this and we get this area under the curve, and that represents the area of the circle. Anyway, so from before we discussed how then the area is equal to the integral of h of x dx. And then we put bounds on this integral. What does x range between as we integrate these slices? So which values do these slices lie over? So we integrate from what to what?
Is it R?
Yes. So that's the upper bound, and the lower bound is
Negative R?
good. Thanks. And sure. So we have this integral now, and we can write it as twice the integral from negative r to r of the square root of r squared minus x squared. Now, there's one other reason that I'm doing this integral today as a starting example, apart from the fact that it's pretty cool that we can now, for the first time, so this is the first time in your lives that you're actually going to see a precise determination of what the area of the circle is without quoting the formula. We're going to derive the formula using calculus. So that's cool. But apart from that, I also want to refresh your memory on how substitution works with definite integrals. In other words, how bounds change while we substitute. So if we have this expression, we're going to make a trigonometric substitution. What trigonometric substitution is that going to be? Let's And it's going to be x equals something in terms of u. The expression here is of the form a squared minus x squared, right? So what substitution do we make in this case?
Was it cosine?
Yes. So typically both cosine and sine work. Sine is a bit nicer. But it's not just going to be sine. It's going to be a times sine because we'd like to match this a squared. Well, in this case, it's r. So let's use r sine theta. R sine u. Now, at the same time, cosine would also work. The problem with cosine is that its derivative has a sign. It's negative. And so if we use cosine instead of sine, we just have a negative sign floating around, and it's easier. Both it's cosine squared plus sine squared is equal to 1. So if we rearrange it, we can take either one to the negative sign, so both substitutions work. Dx then is our cosine u. This is why we choose sine instead of cosine. Du. And now we want to know how the bounds change. Well, if x is r sine u, then what is u equal to? U is equal to the arc sine of x over r, right? And this is really the substitution that we're making. U equals arc sine x over r. And so this integral becomes 2 times the integral. And then how do the bounds change? We take the function g that we're substituting. So u equals arc sine x over r, and we plug in these values. So we get arc sine -1 to arc sine 1. Then we get the square root of r squared minus r squared sine squared. And then we get times r cos u du. So any questions about that? How the bounds changed?
Can you just state it again, please, how it happened?
Sure. So we're making the substitution x equals r sine u. But in general, when we discuss how bounds change, we need to know what function, this is in the frame of the discussion that we were having last class was what g is in that exposition. It only makes sense if you remember exactly what I use g for. So that's probably a bad thing to say. But the point is, with the new variable that we're introducing, we need to write that as a function of the old variable. So here we're making the substitution x equals r sine u, but we want to know what the new thing is in terms of the old thing. So we have to solve for u in terms of x. And so in effect, we're doing this substitution. This is just a different way to write it. Well, now that we know what the new function is in terms of the old function, what happens when we make the substitution is that we're now integrating with respect to u, but the bounds as u bounds, these are bounds as u, range not from -r to r, but from arc sine -1, which is -r divided by r, to arc sine 1, which is arc sine of r divided by r, right? So we're going to do another substitution soon, and we're going to see how the bounds change again. So we'll see this in a second. But it just new variable that you're introducing, function of the old variable, you do the substitution as you usually would, and the new bounds become this function applied to the old bounds. Does that make sense?
Yes, thank you.
Okay, good.
I'm still confused about changing the bounds.
Right. Let me, well, first let me make this page bigger. And then I can actually review this. So let's just do a quick recap. So we're going to pause this calculation for a minute and just do a recap. So what does substitution look like in general? The general form of substitution is that if you have f of g of x times g prime of x dx, that this integral is the same as, well, okay, if we had this, then we would write let u equal g of x, and then du is equal to g prime of x dx. And so this integral becomes the integral of f of u du. And suppose that this is equal to capital F of u plus c. Then when we substitute back, we get f of g of x, right? Plus c. Now imagine that this was a definite integral. So f of x is equal to the integral of f of let's say x dx. And then I can write u here as similarly. Well, then the if we had bounds from a to b of f of g of x times g prime of x dx, then we know what the antiderivative is. It's f of g of x, right? So this definite integral would be f of g of x evaluated from a to b, right? But that's the same as saying f of u evaluated from g of a to g of b. So the endpoints that we're just going to plug in are g of a and g of b. That's the same as plugging in the endpoints a and b into the function f of g of x. So instead of doing this step in indefinite integral, where we change the bounds, what we do instead is we say that the integral from a to b of f of g of x times g prime of x dx is equal to the integral from g of a to g of b of f of u du. And then you just solve this in terms of u, and then you don't plug the formula for u in terms of x in. Instead, you just evaluate it at these new bounds. So this is how we handle substitution when we're dealing, when we're working in the world of definite integrals, integrals that have bounds. So in other words, if we're making a substitution of the form u equals g of x, then the bounds change as the function u of x. So the bounds become g of a to g of b. Does that clarify it?
Yeah, I think that helps. Thank you.
And so back in this example, we wrote let x be r sine u, but we didn't write what u was in terms of x when making the substitution. Well, we need to know what u is in terms of x. So we need to solve for u, and it's arc sine x over r, and that's how the bounds change. So when you're making trig substitutions, you need to remember to get u in terms of x before you apply it to the bounds. That's the main point here. Because here we've said how the bounds change when u becomes g of x. Well, here we're not saying what u is, we're saying what x is in terms of u, but you can solve for u in terms of x. Okay, I'm going to do this magical thing where I just push all of this down and continue this calculation here. Any other questions? Okay, let's recap very quickly what the arc sine function is so that we know what those bounds are. So if I'm to draw the sine function, this is its maximum point. What is this x coordinate?
R.
This is the function just sine of x. So sine of x is equal to 1 when x is equal to. So it doesn't depend on r because we're just talking about the function sine x. I just wanted to review details about the arcsine function.
Pi over 2.
Exactly. To minus pi over 2 at the bottom side. So what happens with the arcsine function is that we take this function and we reflect it across the 45-degree line. That's how we form an inverse function. And the graph of arcsine looks like this. So it's a reflection of the function of sine. And then if this point were pi over 2 comma 1, this point right here becomes 1 comma pi over 2. Its reflection across the 45-degree line exactly swaps the x and y coordinates of every point on the graph. So in other words, arcsine of 1 is equal to pi over 2. And arcsine of -1 is equal to minus pi over 2. So this is just a quick review of what the arcsine function is. Now there's an r here that doesn't depend on use. That's just a constant, so we can take it out of the integral. So this becomes 2r times the integral from minus pi over 2 to pi over 2 of, well, actually, we can take another r out because there's an r squared inside of this square root. So I can write 2r squared. The square root of 1 minus sine squared u cos u. And the 1 minus sine squared becomes a cosine squared by Pythagoras. And so I get just the integral of cosine squared u du. Any questions about that? So now continuing, I'm going to take this integral and I'm going to do the trick where I have that 2 cosine squared x minus 1 is equal to cosine 2x. So cosine squared x is equal to 1/2 1 plus cosine 2x. So we discussed this trick last time, and it's also part of homework 3. I ask you to do several integrals of this form. So when I have this half factor, it cancels out. So I get r squared times the integral. So see the 2 went away, of minus pi over 2 to pi over 2 of 1 plus cos 2x. Sorry, cos 2u du. And just to practice making substitutions and changing bounds, let's actually make a substitution here. Let's say, w is equal to 2u, dw is equal to 2 du. And then how can I write this in terms of w? So first off, du is half dw, so I'll introduce a factor of 1/2 in the front. And then what does the body of the integral become? Oh, sorry. Of course, the main point of this was to show you how the bounds change, and I didn't change the bounds. First off, what do the bounds become when we have the function 2u? It's not minus pi over 2, it's now
Just minus pi
yeah,
and pi.
okay. And then the body of the integral becomes, in terms of w,
1 plus cosine w.
exactly. And this is easy to integrate. So that becomes 1/2 r squared. Then the integral of 1 is just x, well, w. And the integral of cosine w, well, the derivative of sine is cosine. So sine of w. And then we evaluate this from negative pi to pi. Now, if we look at what sine is 0 at 0 and pi. So the sine does not contribute in any way. And what we get then is 1/2 r squared. And then I can write this as, I guess, pi plus 0 minus pi plus 0, which gives me pi r squared. So there, we've used calculus and we've actually used trigonometric substitution. So we used some of the more tricky tricks that we knew. And those tricks let us compute what the area of the circle is. There, you, for the first time in your life, actually seen a fully explicit, fully detailed demonstration of why the area of a circle of radius r is pi r squared. Any questions about that?
I have a quick question. It might be a stupid question, but for where it says let w equal 2u, is there a specific reason that w is the variable, or is it just, does it not have any specific?
Oh, so we've already used u, right?
Mhm.
So after I've used u, the next letter that I use is w. That's just my convention. You
Okay,
can't
so it's
write u equals 2u because u is already in use. So when you have x, you make a substitution for u. When you have u, you make a substitution for w.
okay. Thank you.
And then after w, you choose whichever other letter you want, so long as it's not a un or w. On the other hand, for parts, even if it's in terms of u, I'll write u and du and w and dw, because we're not actually introducing a new variable. So for parts, sometimes I'll write the justification as u equals something in terms of u, but that's because we're not making a substitution. Although I'll try and not make that case arise. So the fact that w is actually w matters because we're going to use it as a variable here. You could use any other letter, but the point is that we're introducing this. For parts, on the other hand, the u does not appear in the integral that you get when you do parts. So there, du and du are just formal specifiers for specifying how you're doing parts, whereas here you actually need to know what the u variable is. So the next line depends on the fact that I put a w here. That's why I have a w there. Any other questions?
I just had a question about when you change the bounds, what is the relationship? Like, how do I know what I substitute in is going to change? Like, how is it going to change the bounds, I guess?
So when you substitute something in, if you're introducing a new variable, then the way that the bounds change is that your new variable is going to be a function of your old variable, right? So here w is a function of u, right? And so my integral, these are u values, but now these are going to be w values. And the W values are what happens when I apply this function to my original U values. Earlier before, I had the bounds -r to r. Those were X values. Then I introduced a new variable U, and U as a function of X was this. And now I'm writing the integral in terms of du. Well, what are the U values? Well, the U values have a certain dependence on what the X values are. Do you understand what I mean by U value and X value? It's not fully rigorous, but
Yeah, no, I think I understand.
right. So now that we're integrating with respect to U, I want the bounds to be U values, not X values. But I have a formula for U in terms of X. So I use that formula. Now here, the integral is now in terms of W. So I want W values, not U values. Well, I have a formula for W in terms of U. So I transform my U values into W values using that formula. In this case, twice. It just doubles what the previous values were.
Oh, okay, I see. That makes sense. Thank you.
Right. And then the abstract, just indefinite function exposition of it is this. If you make the substitution, let U equals G of X, then the bounds change to G of A and G of B. But we also had to remember that earlier before, when we do trigonometric substitutions, we write them the other way around. We write X equals something, not U equals something. So you have to solve for U before doing it. Okay, good. So everyone should be pretty impressed because we've just derived the area for the formula for the area of a circle. And you need trigonometric substitutions in order to do this. So you may ask, well, what's the point of learning trigonometric substitutions? This has nothing to do with things that you actually care about. Well, here, bam, we've just derived the formula for the area of a circle and it has used trigonometric substitutions. So I think that motivates trigonometric substitutions pretty well. And then we're going to see examples from physics later on where these substitutions come in as well, because determining the area of the circle might still be a pretty abstract problem. Now, I'm going to jump a bit ahead and then I'm going to backtrack. Now let's do the volume of a sphere. And in general, if we have some region in 3 space, and we slice it up according to XY slices. Into, let's say, X slices. And each slice has area A of X. Then the volume of the region is and then I could write V equals, and let's say these X slices with X ranging from A to B. Then what is the volume of this region? So to draw a picture, sometimes I draw a 3 space like this. So this axis is going into the blackboard. I usually use X, Y, and Z as my axis labels. Then in this case, we were later on going to determine what the volume of a sphere is. So you can imagine some sort of sphere in 3 space. This gives it the impression of volume. And then you can imagine that at every single point X, I have a 2-dimensional slice over this point X. And I found the areas of each of these slices. how do I combine those areas to get a volume? Well, I should integrate it, right? I should integrate from a to b of a of x dx. A is a function of x. And so this is a generalization of what we had before. Well, it's a higher dimensional version of what we had before. Before we had heights, and we said that if we integrated the heights, then we got an area. Well, here, if we have area slices and we integrate all of the area slices, then we get a volume. So it's the same thing, except now instead of knowing what the height is, here we just needed this height, right? Here we integrated the height h of x dx from the areas in which it were bound, and that gave us an area. Well, here we want to integrate the areas over each area slice. So let's do an example. What is the volume of a sphere of radius r? So this is bound by the surface. This is the area. This is the volume, or this is the region. Is it I? Right. Unbound by. Let's say x squared plus y squared plus z squared is equal to r squared. And then what are the, so I drew it right here, a picture. Well, we all know what a sphere looks like, right? So imagine that this picture actually is a sphere in three-dimensional space. And then imagine that we have some axis going through the center of the sphere, and we're going to call this axis the x-axis. Then at every single point, I'm going to take the plane that is perpendicular to this axis, and I'm going to get an area in that plane. What is that area going to look like? What do all of these cross sections look like? So if I slice a sphere with a plane, what is the picture that I get on the plane?
A circle?
Yeah, exactly. And we can tell what circle it is if we fix a certain x value. If we fix x to be a certain value, then the equation becomes so these are the sort of YZ planes. It becomes y squared plus z squared is equal to r squared minus x squared, right? If I just rearrange this. So the plane, the slice over x at x is a circle of radius the square root of r squared minus x squared. Because in general, the circle is of the form x squared plus something squared, the two coordinates squared is equal to r squared. So here the radius is the square root of r squared minus x squared. But then we can say what the area is. Thus, the area at x is equal to pi times, let's say, radius as a function of x squared, right? And the radius is this square root. So the area is going to be pi r squared minus x squared.
And why is that not radical? Why is that in parentheses?
Because the area of a circle is pi r squared, right? And what is the equation of a circle is x squared plus y squared is equal to r squared, right?
Mhm.
So if I solve the equation for a sphere for a certain x value held constant, then this is r of r squared at x, right? So we have that r of x is equal to the square root of r squared minus x squared.
Okay, so that's why it got rid of it, and that's why it's the pi times the r squared minus x squared in the parentheses.
Exactly.
Okay, thank you.
So what we've determined then is that if I take the sphere and I take this point x and I take the slice over x, then what I get is that that area is pi r squared minus x squared. Another way to think about it is if we look at the xz plane. So this is x, this is z, and then the y axis, it goes into the blackboard. This slice is going to be a circle of radius r, right? And now at a certain x value, I have this. I want to know what the radius of the circle is. I need to plug in my laptop. Well, then the cross section over x looks like this circle going into the blackboard, right? Well, what is the radius of the circle? The radius of the circle is this height here. And before we solve for what that height was, before we solved that that height was r squared minus x squared, right? So this height, r squared minus x squared, becomes the radius of this circle right here. Well, sorry, the square root of r squared minus x squared. And then we square it and we get pi r squared minus x squared. So then I can solve for the volume. The volume is the integral. What do the x values range over?
R and R minus.
Good. Of pi r squared dx, which is, or rather I should actually I shouldn't write that formula. I should write it's the integral of the area slices dx. And then I have an expression for that. It's pi r squared minus x squared dx. And this is an easy integral. So this is pi. Then I have r, so it's with respect to x. So this is r squared x. And this is minus 1/3 x cubed. And then I evaluate the bounds negative r to r. And so that becomes pi. And then I look at this. This becomes r cubed minus 1/3 r cubed minus, and here's the thing, both of these are odd degree. So when I plug in negative r, I get minus r cubed. And here I get plus 1/3 r cubed, because the cube of negative r is minus r cubed. And then if I recombine those, I exactly get pi 2r cubed minus 2/3 r cubed. And I can then rewrite this as pi r cubed. And then I have 2, which becomes 6/3 minus 2/3 And so that becomes 4/3 pi r cubed. And that is the volume of a sphere. We've just derived the formula. Again, it's the first time in your lives that you've actually seen this formula derived. So that should be pretty exciting. And this integral wasn't as bad as before. We didn't have to do a trig substitution. It was just a regular polynomial, right? Okay, so that's how I wanted to start the lecture. Now that we're discussing areas and that I jumped a bit ahead to volumes, calculus lets us find out what the area of a circle is and what the volume of a sphere is. And it's not that bad. The area of a circle turns out to actually be harder to find than the volume of a sphere. Well, for the volume of a sphere, you need to know what the area of a circle is. So it's incremental. But knowing the area of a circle, the volume of a sphere is pretty easy to determine. Okay, so let's step back and do some more area problems before we jump ahead into volume. So here's a problem. Find the area between the graph between f of x equals sine of x and g of x equals cosine of x on the interval 0 to pi. Or let's say over the interval. Okay, now before I said that you would need to determine which function was bigger than the other, and that could be done by solving for the intersection points, then plugging in points and seeing which function is bigger. So you do not always have to do that because you can start the problem by drawing a picture, and then the picture might make it clear what the situation is. So in this case, the graphs of sine x and cos x, we know how to graph these functions. So starting by drawing a picture will suffice. So we start by drawing a picture. And we can draw this picture because we definitely know what the graphs of sine and cosine look like. So let's plot sine. Here is pi. Sine goes from okay. That's my best attempt at drawing the sine function. And then let's draw the cosine function. Right, so this is the interval 0 to pi. And then now that we've drawn this, we can look at the area that's in discussion. So it's the area bound between these two curves. So we want to find the area, if I'm going to shade it in, of this region. And now we know that there's going to be one intersection point. There is one intersection point. So what is the value at which sine and cosine agree early on in their graph? Well, remember the 45-degree triangle? Here, the two sides are equal, right? So what is 45 degrees in radians?
Pi over 4?
Exactly. And then we can be sure that there are no more intersection points, and we can be sure which function is bigger than the other because we all know how to graph the function sine and cosine. So we're not going to plug in values to determine which function is bigger from the graph. We know. So if I look at the blue one is that is sine. So the blue one is F and the green one is G. So we know that G is greater than or equal to F on the interval 0 to pi over 4. And F is greater than or equal to G on the interval pi over 4 to pi. So we started by graphing. That's important. Drawing a picture is always a good place. And then from the picture, it might be clear which function is bigger than which function and when. So then given this, thus the area is, and then we just write down the expression that solves it. It's going to be the integral from 0 to pi over 4 of what? So G is bigger than or equal to F. What are these heights over this region?
One.
Well, I mean, as a function of X in this region. We're going to subtract one function from the other, and what do we get?
G of X minus F of X.
Yes, and in particular, G is cosine X and F is sine X. So we get cosine X minus sine X. And then plus the integral from pi over 4 to pi of the other difference, sine of X minus cosine of X dx. So that's what the area is. And we can write that that's equal to, well, then let's just do the first integral. What is the integral of cosine?
Sine.
Yep. And then the integral of minus sine is?
Cosine.
Yep. And then, so that's the first integral, and then we evaluate it from the bounds 0 to pi over 4. And then the second integral, well, I'm not going to ask you to answer that because it's just minus the original function. So you know what, we could write minus, that factor comes out from here, minus sine of X plus cosine of X. And then evaluated from pi over 4 to pi. Okay, so then we just look at what those values are. Well, we know what sine and cosine are at pi over 4. What is this? So this point is pi over 4. And then do you remember what the sides of a 45-degree triangle are?
Root 2 over 2.
Good. Yeah, root 2 over 2. So both sine and cosine at pi over 4 are root 2 over 2 plus root 2 over 2. And then we look at the values at 0. Well, at 0, g, which is cosine, is 1, and sine is 0. So then we get 0 plus 1. So that's the first integral evaluated between the bounds. And then we have the second one. And then we have at pi. Well, what happens at pi? At pi, cosine is -1 and sine is 0. So here we get sine is 0 and cosine is -1. And then what do we get at pi over 4? Well, we've already done that. It's √2/2. Plus √2/2. Okay, let's look at what we get overall. So here we get √2 minus 1. And then we have a -(-1), so that's a +1. And then we have a minus √2 twice this, so plus √2. And so that overall, that becomes 2√2. So that's a fairly nice expression. And we now know from calculus that this shaded region has area √2/2. So less impressive than determining what the volume of a circle or a sphere are, but cool facts. So that was a mystery that no one knew needed solving, but damn if it didn't just get solved, so good work. Any questions? Okay. Let's do the next problem. So now it's going to get slightly more interesting. Find the area bounded by the x-axis and the curves f of x equals, you know what? I'm not going to actually write f of x and g of x. I'm just going to give it in terms of, I'm not going to give the I don't need to give the functions names f and g. I can just write by the curves y equals x squared. So the difference between writing f of x equals x squared and y equals x squared is that I'm just not introducing the name f. I'm going to leave the functions anonymous. And the reason that I'm doing this is because in some problems it'll be given like this, in some problems it'll be given in terms of f and g. And I don't want to always do it in exactly one way. And y equals 2 minus x. So this is a line, and this is a parabola. And those are functions that we know how to graph in high school. So the best way to start is by drawing a picture. So let's start with this line 2 minus x. It is equal to 0 when x is equal to 2. So if this is 2, then when x is equal to 0, this is 2. Let's say this is 2. And the line looks like this. And then we have the parabola, which is 1 at 1. And so we want the area bounded by the x-axis and these two curves. So the area that has these three things as its sides is going to be this shaded area right here. This is the unique region bound by all three of these. Now, there are two methods for solving this problem. So first, I'm going to give two methods for solving this problem. So here is method 1. Any ideas for how we'd find this area?
Can you set up two integrals, but one for each function? Like the first one?
Yes, exactly. So we take this region right here and we divide it into 2 pieces. Divide it into 2 parts, 2 regions. Is region spelled with an E or an I?
Region.
I. Okay, thanks. I am terrible at spelling. Abysmal. So here is our function. Here's our area. I'm going to draw it all in one color. And what we can do is we can split it like this. And I guess let's color this area in blue. And let's color this region in red. And we know what the coordinates of this point are. So just by inspection, at 1, y is equal to 1. And this is also 1. So this point is 1, 1. So on the x-axis, this would be 1, this would be 2, this would be 0. And then from the graph, we get this from drawing the graph. And then we're going to write that the area is the integral from 0 to 1. And then what are the heights here? So the functions, I remind you, are x squared and 2 minus x. So in the first region. I heard some people unmuting themselves, but no one's speaking. Okay, there's only background noise. Anyway, this function, it's the green function, right? It's the x-axis and the green function. So the minus the other function would be 0. It's just the function x equals 0. And then this function is y equals x squared. So the heights here are just x squared. And then this is the integral from 1 to 2 of this function. Well, what it is its bound. It's 2 minus x dx. Also, there is some, 1 second. I'm just going to quickly mute everyone because there was some background noise. Okay, there we are. Now, these integrals are easy. So this is the integral of 1/3 of x cubed from 0 to 1. And this is 2x minus half x squared from 1 to 2. And then I can do that, no problem. Okay, so here I get 1/3 x cubed minus 0. And here I get, so 2 by 2, that's 4, minus, this is x squared 4 over 2, 2, minus, then I plug in 1, so I get 2. And here I plug in 1 and I get minus 1/2. So here I have 4 minus 2, so that goes away. And then here I have a 1/3. And here I have a minus 1/2, so plus 1/2. And then I can write this as 2 over 6 plus 3 over 6, and then I get 5 over 6. So this is the first method. This is a more complicated region. And when you draw the picture, you realize that you have to split it into two different areas because there are two natural ways that the formula for a height is a piecewise function. On this part, it's given by this function. On this part is given by the other function. And so that's why I have to split it into two integrals, because the formula changes. Any questions about that? So there is a second method that you can do instead of this, method 2. How would I do this without splitting it into two regions? Well, okay, yeah, it's hard to think about it if you haven't seen it before, but it's integrate with respect to y. Oh, wait a second. I did unmute all before. Are people able to unmute? I think everyone should be able to unmute themselves though. Okay. So hopefully we're not in a situation where, yeah, it appears that you can. So the idea here is that instead of doing X slices, we're going to do Y slices. So if we look at this region right here, and let's draw the y-axis right here. Then what we can do is we can imagine marking some point y here, and then looking at the width or the length of this slice. And then we can sum up these lengths right here. And if we look at our functions y equals x squared, and y is equal to 2 minus x, then we can rearrange them for this curve. This curve right here can be described as the function x equals square root of y. It's the positive square root. And this can be described as the function x equals 2 minus y. Right? So if I rearrange this and solve for them. And then it's clear that the one which has the larger x value as a function of y is the line, just from the picture. So I can write that the area is, and now what are the bounds? What is the y value at the top?
One.
Yep. So I can write this as an integral with respect to y from 0 to 1 dy. And then what's the expression on the inside? Well, here is the upper x value. It's 2 minus y. And then I subtract this lower x value minus the square root of y dy. So why is this? Because I can say, for example, the length of these segments is a function of y, r. So let's actually erase this for a second and say what the length is. If this is y, then the length of y is 2 minus x minus the square root of, 2 minus y minus the square root of y. If you look at these blue slices and you ask what is the length of the blue slice at the y value y, you get this expression just from this picture. And so the area is the integral from 0 to 1 of L of y dy. We're summing up all of the horizontal instead of vertical slices now. And we get the integral from 0 to 1 of 2 minus y minus the square root of y. And this is an easy integral because it's just a power rule for each one. So this is 2y minus half y squared. And then this is y to the power of 1/2. So I'm going to get, well, there's going to be a minus sign because it's this, y to the power of 3/2 and then 2/3 dividing by that coefficient. And I'm going to take all of this and I'm going to evaluate it between 0 and 1. Well, at 0, I get 2. Then I get, sorry, at 1, I get minus 1/2 and minus 2/3. And then when I plug in the value y, well, look, all of these are powers of y. So I just get 0 here. Then I want to write this under the denominator of 6. So I get 12 over 6 minus 3 over 6. And then I have to multiply top and bottom by 2. So I get minus 4 over 6. 3 plus 4 is 7. 7 minus 12 is 5. And does that agree with our previous answer? Yes, it does. So that is a good sanity check. We did it right. So the moral is that sometimes it's easier to integrate with respect to y. Well, it's in this example, they were about the same difficulty, but they're two different methods. Okay. Oh, good. So we've spent an hour and a half. So let's do a break right now. Let's do 2 breaks today. Because again, I'm padding out the material because I definitely don't have 3 hours worth of lecture prepared. So let's take a 12-minute break until, so +2 is 25 and then to 35. Resume at 7:35. Sounds good? Okay, see you then. Okay, let's resume. Right, so now on to more volume problems. Wait a second, is this connected? Okay, good. On to more volume problems. So in calculus B, there are a lot of problems concerning regions of revolution or volumes of revolution. And what these look like are this. Suppose you have something like a function that looks like this. So take this region and revolve it. If we revolve, rotate, so imagine that there's a third axis. So now it's going to be three-dimensional. This is the region over the sort of XY plane. Now they're labeled in a different way. And if we rotate it around the x-axis, we obtain a region that looks like this. So at every single point, we have a circular region that we obtained when we rotate it. And so it turns out that calculus, what type of integrals that we've learned are particularly good at solving this type of problem, finding the volumes of regions obtained by revolving some region around an axis. And so every single calculus B course spends quite some time on how to compute the volumes of these regions. Let's say if we rotate this region in 3 space around, let's say, the x-axis. And that's in this case. We get some volume. Or we get some, let's say, three-dimensional region. And we want to find its volume. So to give an example, as a first example, the region between the graphs, the graph between the graph of f of x equals 2 plus cos x, and the x-axis over the interval 0 to pi is revolved around the x-axis. Find the volume of this region. Of the region formed. And so a good way to start any word problem, and particularly these problems, is to draw a picture. And this picture we can draw easily because we know what the graph of cosine looks like. And so we know what the graph of 2 plus cosine looks like. It's just shifting it up 2 units. So let's say this is 2. This is 3. Then from 0 to pi, cosine looks like this. And let's say this is 1. Right? So this is the graph of 2 plus cos x. Then if we imagine what it looks like when we revolve it, what we can do is we can draw this graph reflected below the x-axis. For some reason, it's harder to draw it upside down. Although it's just also a cosine wave. Okay. And then if we look at what the region looks like, it looks like this. So can everyone picture that? I got a thumbs up. Good. And so the question is, how do I find the volume of this region? Well, we're going to do so via x slices. So first we draw the picture. So that's done. Let's do a different color. And now we determine the area of the x slices. So what happens is we have a certain x value and we rotate this around. And when we rotate it around, we obtain a circle. So in general, a of x, if this is the function f of x, a of x is going to be a circle, the area of a circle of radius f of x. So we can write that a of x equals pi f squared of x. And this will be something that'll hold generally when we look at regions without cavities. Later on, we're going to do regions that have a hole in the middle of them. But if there's no hole, then you just set it up like this. A is pi f squared. So if we look at this point right here, this point has coordinates x comma f of x. And so this circle right here, that is a circle of radius x. A circle of radius f of x. And so the region of that's the area of that x slice is pi r squared, where r is f. And this is why it was good to start this lecture by finding what the formula of a circle is, because now we can use that for lots of different problems. Okay, so now we can set up this integral. Thus we have that the volume is the integral. And now we're looking at the x slices. Well, we care about the x slices from 0 to pi because that's given to us. Of pi of, well, let's write it twice. Pi of f squared of x dx, which is equal to the integral from 0 to pi. Let's bring this pi out front. And now we have 2 plus cosine of x squared dx. Now we expand that out. 4 plus 4 cos x plus cosine squared x dx. And now we've already done the integral of cosine squared before. Well, actually, let's let's do the substitution. Let's remind ourselves how we do the integral of cosine x, and not the substitution, the expression for it. So I can rewrite this as 4 plus 4 cos x plus 1/2 1 plus cosine 2x. Right? And now I can write down the antiderivatives of these expressions. So the antiderivative of 4 is 4x of 4 cos x. What's the integral of cosine?
Negative sine.
The derivative of sine. So derivatives are always well behaved with the functions that begin with the letter s. So the derivative of sine is cosine. The derivative of secant is secant tan. Whereas if you switch the letter, the derivative of cos is negative sine. And the derivative of cosecant is negative cosecant cotan. So as far as derivatives are concerned, the functions that begin with s are better. Similarly, the derivative of arc sine is better than the derivative of arc cos because it has arc cos has a negative sign. But for integrals, it's the other way around. The c letters are better. So because it starts with a c, we don't have to introduce another sign. It's just sine of x. And then I have 1/2 x. And then I can do this antiderivative by inspection. If I look at the derivative of sine of 2x, I get 2 sine 2x by chain rule. So I should introduce another factor of 1/2. So I get 1/4 sine of 2x. Foregoing the substitution and just doing it by inspection, because I did it by substitution before at the first example of the class. It came up when we were finding the area of the circle, right? So, okay, let's plug in the values. We get pi, and then we get 4 pi. Now, sine of pi is equal to 0 plus 1/2 pi. And then sine of 2 pi is also 0 minus, okay. So 4 times 0 is 0. Sine of 0 is 0. Are we really happy? Yes, we're really happy. This is 0 and this is 0. So minus 0. And so we just get pi squared times 4 plus 1/2. And we can rewrite 4 as 8/2. So we get 9/2 pi squared. So this is a traditional a volume of revolution problem. This is a very by the textbook problem. And in general, when you're doing it, you'll get an expression of this form, a equals pi f squared. So if there's no cavity, and what do I mean by cavity? I'll explain in a second when we do the next example. But if there isn't a cavity, you just set it up like this, and then you just do the integral. And now sometimes some functions are a bit annoying to square. Here you have to FOIL it out, and then you integrate each piece. And then again, see, doing things like the integral of cosine squared, it comes up a lot in practice. We've already had this come up in 2 examples. Okay, so that's a good example. Let's do the next example. So how did I write it? I wrote it like this. The region between let's divide these with a line. The region between f of x equals cos x and g of x equals sine x over 0 to pi over 4. so we saw this example before, is revolved around the x-axis. Find its volume. Find the volume of the resulting region. Okay, so let's start by drawing the picture. And this picture we drew before. So if we have cosine, then it meets the graph of sine at pi over 4, comma root 2 over 2. So this point right here, it's pi over 4. And then this coordinate right here is root 2 over 2. And this is 1. And now if we take this region and we mirror it, then when we revolve it, well, we just get a circle here. But here we get regions which in calculus textbooks they call washers. So the x sections look like, and then if I was going to draw a picture, it would be 2 concentric circles. Well, I drew the green one on the outside, so let's draw the green one on the outside. And then the blue one on the inside. And apparently I'm shading this region in red. So in calculus textbooks, these are called washers. Because calculus text, well, okay, knowing what a washer is not something that only old people know. I mean, it's when you're screwing something in and then you have something to support the screw. But that is not also the mathematical terminology. It is very old-fashioned terminology. The mathematical terminology is an annulus. This is an annulus. And the plural is annuli. Annulus. I'm not sure if I'm spelling it right. I'm bad at spelling. The point is these are concentric. It's bound by 2 concentric circles. And so we can get what the area of this region is. The area as a function of x, it's going to be the outer circle minus the area of the inner circle. So it's going to be pi. What's the outer function? The outer function is the function, the green one. So that's cosine f of x, pi f squared of x minus g squared of x. This is assuming that f is greater than g, which it is in this region, right? Does that make sense? So then I can write down. Any questions? Well, okay. I'm going to integrate the area of these annuli, the areas of annuli from 0 to pi over 4, which are the bounds in the question. Of pi, and then I have my 2 regions. So cosine squared minus sine squared x. How can I rewrite the expression in the middle? What does cosine squared minus sine squared equal to?
One?
Cosine squared plus sine squared is equal to 1.
Oh,
But
yeah.
the difference, that's an identity that we had before. So this is equal to cosine of 2x. That's something that you should remember. The double angle formula for cosine, right? We've used it a lot in this course. So good thing to keep in mind. So yes, cosine squared minus sine squared is equal to cosine 2x. And then, you know what, let's do it with substitution to remind ourselves how to do it. Last time we did it by inspection as to what the integral was, but let's do a substitution. Let u equal 2x. Du is equal to 2 dx. Then I get a factor of 1/2 because of this. Then the bounds change from 0 to pi over 2 cos u du. Now the integral of cosine is sine. And then the bounds 0 to pi over 2. Okay, well, so sine of pi over 2 is equal to 1. Half pi. Okay, sine over 2 is equal to, is that just it? Yeah, 1, and then sine of 0 is equal to 0. So I get pi over 2. So that's an interesting, it's interesting that this, I did the problem because it came out to a nice expression. These problems aren't just randomly chosen, they're chosen to be nice. So yes, that's what it comes out to. So this is a generalization of the previous technique. In the previous technique, we were just revolving something with nothing, no hole in the middle. But if in general, if there's a hole in the middle, then the cross sections don't look like circle, they look like annuli, which means you have to subtract the area of the smaller circle from the area of the bigger circle. And so you get an expression like this. So in general, when you have this method, which calculus textbooks call the washer method, so this is the washer method. Then you will get a formula that looks like this, and you integrate that. Okay, let's do the next example. So now, let's say we rotate something around the y-axis. Let's say that we have the region enclosed by the x-axis. And f, or let's say, and the graph of y is equal to 2x minus x squared is rotated or revolved around the y-axis. Find the volume of the resulting region. And as always, we're going to start by drawing a picture. So if we look at this equation, y is equal to 2x minus x squared, that's factored as x times 2 minus x. So it's a parabola that opens downwards and it has roots x and 2. So if we look at the area bound by this curve and the x-axis, then the air region in question is this region right here. And what we're going to do is now we're going to rotate it not around the x-axis, but around the y-axis. And so what we get when we do that is, let's say I reflect it, I'm going to reflect it in a different color. And then I get a region that looks like this. And then in the middle, I also have these annuli shapes. So can everyone picture that region? I've taken this and I've rotated around the y-axis. So now we get a cake shape. This is cake shaped. Well, it is one shape of cakes. There are cakes that looks like this. I don't remember what that type of cake is called, but yes, there is a type of cake that looks like this. Okay, now the question is, how do I find the volume of the resulting region? And there are two different methods to do this. So let's break it down into two methods again. So method 2 is going to be to integrate with respect to y. To integrate, yes, with respect to y. But method 1 is going to be to integrate with respect to x. But the thing is that if we look at a certain x value, then what do we get? So let's draw this region again. Let's say we fix a certain x value. Then we have this slice over it right here. And when we rotate that slice around, what we obtain is a cylinder, right? And so we have a bunch of cylinders at a fixed x value. The vertical line segments is revolved to become a cylinder. And in calculus textbooks, they call it a cylindrical shell. So this is using standard calculus textbook terminology, which we all follow like members of a cult. Calculus terminology is different from math terminology sometimes. Right. Now, it turns out that we can compute the volume by summing up the areas of these cylindrical shells. Integrating the area of the cylindrical shells. So if this is x, let's say this point right here is x comma f of x. Then the question is, what is the area of this cylinder? So what is the formula for the area of a cylinder? Just the bounding shell, not the top and the bottom. Well, first off, what radius does this circle have?
X.
Yes. So it's a circle of radius x. So the circumference of the circle is 2 pi x, right? So this has a circumference of 2 pi x. And what is the height of this cylinder?
F of X.
Exactly. And so the area is 2 pi x f of x. And this is another general formula that you have. When you're doing things via cylindrical shells, you'll always get this formula, 2 pi x f of x. So to remind you, looking at the formulas that we had in all of these cases before, if you have something without a cavity, then you just get the areas of these cross sections are just circles. So you get pi f squared. If you're doing this, then the area of the cross section are annualized. So you get pi f squared minus g squared. If you're doing this, then they're no longer cross sections. You're not summing cross sections. You're summing areas of cylindrical shells. And the areas of these cylindrical shells are then 2 pi x f of x. So you can derive this formula each time, or you can remember it. But when we're doing the cylindrical shell method, we generally have an expression that looks like this. And so in our case, for our particular function f, the function is 2x minus x squared. So a of x is equal to 2 pi x, then the function is 2x minus x squared, which we can also write as 4 pi x, 4 pi x squared minus 2 pi x cubed, right? So then what is the volume? The volume is given as the integral. Thus, the volume is the integral from what x values does this function range over? Well, this second intersection point is 2, right? So if we look at the parameter over which we're parameterizing all of these cylindrical shells, then they're parameterized from x equals 0 to x equals 2. A of x dx. So that's equal to the integral from 0 to 2. Let's factor out the pi. And then I just get 4x squared minus 2x cubed dx. That has an easy antiderivative. So I get 4/3 x cubed minus 1/2 x to the 4th. And then I want to evaluate this between 0 and 2. And okay, the 0 endpoint, it won't contribute anything. So I'll just get pi. Then I have, when I plug in 2, well, okay, so 2, 4, 8, and then 16, 32, so 32 over 3. Here I wrote down sorry, 2, 4, and is it indeed 4? Yeah. Okay, so 2, 4, 8. And wait, let me just check. Yeah, good, good. We're good. No, we're good. Okay, 8, 16, 32, 32 over 3. Minus, and then it's 2 to the 4th. So that's 16. 16 over 2. Which is 8. But okay, then minus 0. So I don't have to, I can just write this as, okay, this is 8. 8 times 3 is 24. So 30 pi times 32 minus 24 over 3. And then if I'm counting up from 24, I get 6, 7, 8. So 8/3 pi. And that is the right answer. So this is known as the cylindrical shell method for integrating. Any questions? Okay, and then we can do methods 2, which is to integrate with respect to y. Now, let's look at that. So if we look at this, then over a fixed y value, we get an annulus. So if we fix a certain y value, such as this one, then when we rotate it, we get an annulus shaped region. And so we're going to go back to the washer method, so long as we can find what this outer and the inner radius are, right? That is a y, not an x. So we want to find the outer and inner radius with respect to y. For the outer and inner radius, radii, with respect to y. Okay, let's look at what our equation is. Our equation is 2x minus x squared. Y equals 2x minus x squared. So we would like to solve for x in terms of y. Okay. Now we can sing the song and remember what the quadratic formula is. But let's do it for specific values. So this is a is equal to, let's just rewrite this, minus x squared plus 2x. Okay, b is equal to 2, a x equals negative b plus or minus square root b squared 4 minus 4ac. Well, one of them is 0, so that's sorry. Wait. 1 second. I do not want to find the roots of this. I want to solve for x in terms of y. 1 second. This example I don't have in my notes. I just decided to do the second method. Okay, let's complete the square. I'm going off script here, but I'm pretty much done with the material that I had for today. So we are going to do this example, figure out how to do it impromptuly, and then I think that's all for going to be all for today. Okay, let's figure out how we would get this inner and this outer radius. So I'm tempted to just begin by completing the square. This is minus x squared minus 2x. And I can write that as minus x minus 1 squared. Now this would be wrong because I have a +1 here, so I need to say -1. So I can write this as 1 minus x minus 1 squared. So x minus 1 squared is equal to 1 minus y. And so x minus 1 is equal to plus or minus the square root of 1 minus y. And so x is equal to 1 plus or minus the square root of 1 minus y. Okay, there we are. No quadratic formula. What we're just doing is we're solving for x in terms of y, and we can do so by completing the square. That is something that generally works. Let's just sanity check that I did this calculation correctly. Yeah, that looks good. Okay, no quadratic formula, complete the square, which is how one derives the quadratic formula anyway. So what we find then is that if we look at this parabola, it's centered around x equals 1. And these 2 points respectively here, these are the coordinates 1 plus the square root of 1 minus y. Comma y, and 1 minus the square root of 1 minus y, comma y, right? Any questions about that? Okay, so then what do we have as the area of this washer? Well, the outer radius is this and the inner radius is this. So we can write that the area as a function of y is equal to pi, and then we have 1 plus square root 1 minus y squared minus the inner one, 1 minus square root 1 minus y squared, right? So that becomes pi. Then I can expand each of these. 1 plus 2 square root 1 minus y plus 1 minus y. That's this one. And then I'm subtracting 1 minus 2 square root 1 minus y. And then again, plus 1 minus y. Close that paren, and then close this paren. And so only the middle terms survive, and I get 4 pi square root 1 minus y. So that is the area of this washer. If I've solved for x in terms of y, and I found the inner radius, I found the outer radius, and then I took the difference of pi r squared. So the volume then, whoops. is given as the integral. Now, what are the bounds? So we need to know what this upper bound is. When x equals 1, what does y equal to? At x equals 1, y is equal to -1 plus 2 is equal to 1. So this upper bound is 1. So we're integrating, sorry, 1, not y. So we're integrating from 0 to 1 of this formula. Volume is the integral of a of x dx from 0 to 1, which is equal to the integral from 0 to 1 of 4 pi times this, this is a of y dy. 4 pi square root 1 minus y dy, right? And now we can do this by inspection, or we can do a substitution just because it's 1 minus y. So you know what, let's do a substitution. Generally, we don't do substitutions of the form x plus a, but there's a 1 minus y. So let u is equal to 1 minus y, then du is equal to minus dy, right? So we get minus the integral, and then the bounds change from as 1 minus y. So 0 becomes 1. This becomes 0. The minus sign here is because of this 4 pi. Square root of u du, right? A good exercise in how bounds change, which becomes, well, okay, I can flip these bounds and remove the negative sign if I want. So this isn't necessary. I don't have to flip them, but I did want to flip them in this case. Then I get 4 pi. It's going to be u to the power of 3 halves. And then, so I have to multiply by 2/3. And then this is evaluated between 0 and 1. Okay, so u equals 0, 0, and then I just get pi, and then I get times 8/3. And is that what I had before? That is indeed what I had before. So that is nice. So what did we learn from this example? In general, the difference between cylindrical shells and washers, one is converted to the other if you integrate with respect to the other variable. So for example, if in any of the cylindrical shells problems, we instead integrated with washers, then we with respect to the other, if we integrated with respect to the other variable, the cylindrical shells now become washers, and vice versa. If in this problem we integrated with respect to y, then we'd have cylindrical shells, right? But in this example, it's strictly worse to integrate with respect to y, because then we'd have 2 separate cases. Because we have these heights and then these heights. In this example, it's easier to integrate with respect to x in the cylindrical shell method than it is to solve for x and then do washers with respect to y. But either method works, and they produce the same results. Okay, what time is it? It is 8:24. So we had a midterm today, and I mentioned at the start of the lecture that I was definitely going to run out of material this lecture. It's actually hard to prepare things about applications because I'm used to talking about pure math things. This looks still pretty pure, but also all of the books that I'm using, they have terrible examples. And then I have to go through a bunch of examples and say, no, this doesn't work for a lecture. The numbers are annoying. They're like emphasizing using a calculator, graphing things with a graphing calculator, etc. And while the pure math textbooks don't even spend time on this because they're application problems and they don't want to. So Spivak's Calculus is a good calculus textbook, but the discussion of cylinders and washers is an appendix to one of the chapters. and not even dedicated as a separate unit. And in the British textbook that I have, well, it doesn't start from square one. It's like another module, and that module doesn't have area or volume problems. So it's covered in another British textbook that I don't have. So I think that's all for today. Are there any questions about anything that we discussed today? So it was a pretty relaxing class in which we computed a bunch of areas and volumes.
Can I ask one more question regarding the midterm?
Of course.
Are you gonna, once that other person submits their exam, are you gonna be sending out a solution sheet for the midterm?
I will.
Okay, awesome, thank you.
And I think people should agree, if they've done the assignments, that the midterm was about at the difficulty of an assignment, except I put less tricky problems. So on the assignments, I had a gradation of problems from just direct things to more difficult ones. I put it somewhere like in the middle to the easy version of here. There were fewer problems, but it covered multiple assignments. So the length was overall the length of an assignment, but they weren't the hardest problems that I could pose, far from the hardest problems that I could pose in each one of those categories. So I think it was a fair midterm. I spent quite a while thinking about the questions that I would put on this. And then don't worry, the final grades are, I mentioned at the beginning of the class, going to be curved to the stratosphere. So if you feel that you actually solved some integrals on this assignment and that you presented good work, then that makes me happy. And I'm fine giving you a good grade in the course at the end. If you've actually learned something and submitted good work. You didn't have to submit good work for every problem, but if for like more than half of the problems you submitted good work, then that's great. Then I'm happy about the learning outcomes that have been achieved. Okay, so sorry for ending an hour early today. But yes, I was working on several things and I was sick over the weekend with a small cold, and then I was working on several other things. I think there's only one person whose assignment homework 1 I haven't graded. I finally got through homework 1 over the weekends, but I will wrap that up. I think that I'm going to grade the midterm before I grade homework 2, because the midterm is worth more and people care about that more. So hopefully that should be done at a certain point in time. And then I'll post the assignments for tomorrow evening. And there are going to be some integration problems on it just so you don't get rusty. And then there are going to be a bunch of these volume computation problems and also some problems on what I'm going to discuss on Thursday, which is probably going to be polar coordinates. I think that sounds like a good option. Right. Okay. See you on Thursday.
Thank you.